Very well. So what we learned before in elementary calculus, we talked about the derivatives, then we talked about the antiderivative, which is the opposite operation of taking the derivative. So just to recall for you, for any function like y equals to f of x, if you're able to define the limit definition of the derivative, then we can use those shortcuts and take the derivative of the function. We can take the derivative. Well, derivative is an operator. In linear algebra, you're going to see what an operator is and how to apply an operator for different objects that later on you see we're going to work with matrices. So the derivative is an operator. Now, how did we define this operator? It is d over dx. If the function has free variable x, then we're going to take in the derivative with respect to x, and this guy is called an operator. So this operator on function f of x is denoted by d of f divided by d of x, or simply f prime of x. So like defining addition and then subtraction, multiplication, division, they're opposite operations. We can define the opposite operator for derivative, which is antiderivative, or eventually remember that we call it the integral. The opposite operator of the derivative is antiderivative. Okay, antiderivative. Well, remember that to define antiderivative, we take the Riemann summation, then n goes to infinity, and we change that, the sigma, capital sigma, into long s, and we call it the integral of function f. Okay, if we have a function f and we are taking the integral of function f in different branch of science, the integral has a different meaning. Well, sometimes when we are working with integral, one of the simplest example is the area below the curve. Just one instance. Guys, remember that in different branches of science, integral has a different meaning. In physics, you might say, hey, we are looking for the work done, or in electricity, it has a different meaning about the charge. In statistics, it has another meaning. Sometimes the meaning is the area. So we say that, hey, we have x-axis, they have, for example, y-axis, and suppose this function is a positive function. What's the meaning of that? It means that this function is above x-axis. Suppose this is your function f of x. And then you say that, well, I can evaluate the area below the curve. And suppose my x is bounded between two numbers, like a and b. So I have a definite integral, definite area. The area below the graph of f, when x is bounded between a and b, is the integral of function. Again, this is just one of the instances of integral, the area. In other branches, we have different applications. For the integral, we have different names. for the integral, it's not exactly the area. Very well. So now we are saying that, well, this is defined for a function with only one free variable. Now, suppose I have a function with two free variables. How do I define the antiderivative of that function over the given area? There, we're going to talk about the double integral, and eventually we're going to generalize the idea to triple integrals. Very well. So now that we are in multivariable calculus, we have functions in more than one free variable. We're interested in finding the integral or antiderivative of those functions. So now, how to find the integral of function like z equals to f of x and y? This is the question that we're trying to answer. To answer this question, we need to specify the region over which we're trying to take the integral. So you can write down depends on the region. What do I mean by that? We can divide up the region that we are taking the integral over into two specific forms. The first one is just called a rectangular region. So, rectangular region. If you have a rectangular region, what's the meaning of that? It means that that region is defined as A, comma B on x-axis times C, comma D on y-axis. Well, so your x ranges between A and B, and your y value ranges between C and D. These are just numbers. Y range. So how do we visualize that? The visualization is like this. Here you have your x-axis, then you have your y-axis, and then you have your surface, whatever it is, on top or below, z-axis. So this region is going to be part of the domain in xy plane. So we're going to have A to B, A to B, then C to D. Well, okay, my y ranges between C to D. So the intersection between these two is going to be this region down here. Okay, here we go. This continues, and this is this region. So this guy is the interval A to B cross C to D. This is the region that you're dealing with. So where is the function? The function can be just right here. This is your surface. Z equals to f of x and y. What are we trying to do? We're trying to find, in physics language, we are trying to find the volume bounded between this function and this area. So this is C and D. We are trying to find the volume between this function and this region down here. It's not exactly straight line because here you have a surface and the behavior of the surface might be different. So we are trying to find this guy here. This volume, you have some heights. You take each of these heights in a very small, nice infinitesimal, and then multiply each height by its base, add them all together, and define the double integral. So to find the double integral, it means that we are trying to find, in physics sense, the volume of this region, this part, which is bounded between the surface and this little rectangular area here, the volume of the portion bounded between the surface z equals to f of x and y. So here you have your heights. These are the heights. You have the base, multiply them together, and since this is not a flat surface, we don't have the exact measurement, so that's why we have to use the integral. So surface z and the base a comma b times c comma d. Again, this is not a flat surface. It is changing. Based on the value of z, you get different heights. Since z equals to f of x and y is changing, we have to use the integral. So very well, we're going to take double integral. Why is that? Because we have two variables, variable related to x and variable related to y. Okay. So this is the limit. If you want to just use one variable, it's going to be limit of Riemann sum f of x delta x. Riemann sum and your x is changing, but here we have two variables. It's not just one variable. It means that we have to use two Riemann sums. One related to x, one related to y. Here the order is not important for us. Delta x and delta y, and here you have your function f of x and y. As these small regions, these small delta x times delta y's are getting smaller and smaller. So this is delta x times delta y. These base values are getting very small. You are just taking the limit as these values are getting smaller and smaller. Remember the definition of delta x? It was b minus a divided by n. These are getting smaller and smaller as n approaches infinity. The same definition for delta y. This Riemann sum, as n approaches to infinity, it's now defined as the double integral. The double integral of the function, and delta x becomes dx, delta y becomes dy. Well, delta x is related to x, the change in x values. Well, x is bounded between a and b. So A, this is your inner integral, which has to be calculated first. Inner integral. Then the outer integral is related to your y. The outer integral related to y. So y ranges between c and d. So your lower limit is c and your upper limit is this guy. This formula gives us the volume of this portion of the surface bounded between these little region in xy plane. So here's one example for you when you have a rectangular region. When you have a rectangular region, taking the integral is not very hard. We just need to remember our elementary calculus integrals and just start taking the integral. So let's see. Examples. I'm going to write down one example here for you. This example says, find the double integral of function z equals to x minus 3y squared, over the following region. The region R is defined as, well, you have a set of points such that x is bounded between 0 and 2, x is bounded between 0 and 2, and y is bounded between 1 and 2. Okay. The boundaries for x and y are both fixed numbers. It doesn't matter if you take the integral with respect to x first or with respect to y. Both of them gives you the exact same number. So this is my C and D. I'm going to use different colors. This is my A and B, then these are my C and D. A and B, and this guy is C and D. The double integral, remember that, the double integral of a function f of x and y over a rectangular region is defined as dx dy. It means that you can take the inner integral with respect to x. So this is my inner integral. Inner integral first integral. Inner integral, x is ranging between a and b, 0 and 2. Then you take the integral with respect to y, okay? Outer integral. dy, y is ranging between 1 and 2. 1 and 2. There you go. It's not very hard. You have the function here. This guy is equal to the double integral x minus 3y squared dx dy. My x ranges between 0 to 2. Again, this is your inner integral. You have to calculate this integral first. Then you move on to calculate the integral with respect to y, 1 to 2, the second integral. Okay, recall that. The integral of x minus 3y squared dx. Well, here you have x, the integral of x dx is equal to x squared divided by 2. Integral of negative 3y squared dx. Guys, we are taking the integral with respect to x. It means that whatever term has a y in it considers as a constant, a number. So this guy is nothing but a constant. It doesn't have any x in it. It's just a number. So which is equal to copy down the number, negative 3y squared, multiply that by x. So this integral is equal to x squared divided by 2 minus 3y squared x. And since it's a definite integral, we plug in 2, we plug in 0, do the subtraction. Well, if I plug in 2, what do I get? I get 4 over 2 minus 3y squared times 2. If I plug in 0, both of these terms are equal to 0, so I'm not worried about this. So I get 2 minus 6y squared. Where does it go? This is the calculation of the inner integral. So this integral is equal to, I copy down my outer integral with respect to y, 1 to 2, and my inner integral is now 2 minus 6y squared. dy. Now we start taking the integral with respect to y. Very well. The integral 1 to 2, 2 minus 6y squared dy. Well, the integral of a constant to dy is 2y. The integral of negative 6y squared dy, you copy down your negative 6, y to the third divided by 3, which is negative 2 y to the third. So this integral becomes 2y minus 2y cubed as your y changes between 1 to 2. If I plug in 2, what do I get? I get 4 minus 2 times 8 minus, if I plug in 1, I get 2 minus 2, which is just 0. So the outcome is 4 minus 16, which is negative 12. This is my integral. Negative 12. Guys, note that I didn't ask for volume. I just asked to calculate the double integral. We don't have negative volume. This guy doesn't refer to a volume. It refers to something else. We just did the work in pure math sense. There we go. So remember that I mentioned it doesn't matter if you take the integral with respect to x first, then take the integral with respect to y. So I expect you to ask, what if I take the integral with respect to y first? Let's take a look at this. Let us investigate, see if we get negative 12 at the end or not. So now I claim that I'm going to take the integral with respect to y first, then with respect to x, and I get the exact same answer, negative 12. Well, double integral. Now my inner integral is with respect to y, outer integral it with respect to x. I'm going to copy out my function, x minus 3y squared. Take the inner integral with respect to y. Take the outer integral with respect to x. Well, what do I see? This is my inner integral. I have to calculate this guy first, and my y ranges between 1 to 2. After I'm done with the inner integral, I move on to calculate the outer integral, this time with respect to x, well, 0 to 2. Outer integral. So let's see. So let us find the inner integral first. Inner integral. My inner integral is integral with respect to y, while y is between 1 and 2. And my function is x minus 3y squared dy. With respect to y, x is just a constant. It means that you have to copy this guy down. This is equal to the integral. Let's just write down the final answer. X times y minus, here you have 3y squared. You get 3y cubed divided by 3. And your y ranges between 1 to 2. So you can cancel out 3 and 3. Your y is 2. Your y is 1. So you plug in 2 first. 2x minus 2 to the third minus, if you plug in 1, you get x minus 1. So here you get 2x minus 8 minus x plus 1 for x minus 7. This is your inner integral. Goes here. So far we have the integral x ranges between 0 to 2 of x minus 7 dx. This is your outer integral. Let's calculate the outer integral. Our outer integral with respect to x, it is 0 to 2, x minus 7 dx. Well, this is easy. The integral of x is x squared divided by 2 minus the integral of 7, 7x, and x is between 0 to 2. If I plug in 2, I get 4 divided by 2 minus 2 times 7, 14, minus. When I plug in 0, I get 0 minus 0, or just 0. So what I have 2 minus 14, which is again negative 12. So this double integral is minus 12. It doesn't matter if you take the integral with respect to x, with respect to y, with respect to y, with respect to x. You get the exact same answer. Why is that? Because we have the constant boundaries for x and y. So, if we have rectangular regions, it means that they're super lucky. Everything is easy about rectangular regions. You don't have to worry about anything. You saw that you can take the integral with respect to x, with respect to y, and it gives you the exact same value. Again, remember that it's not always finding the value. Some other times we are finding, for example, different types of quantities related to the topic that is given to us. In math, our main goal is to present different techniques to solve different problems. We're not really worried about what the application is. We just mainly want to try to come up with best technique that help us to solve that problem. Okay, perfect.